So when a wave meets a boundary, what happens? All right? Well, to the transmitted part. What happens to the transmitted part? What changes? What stays the same? Well, if it's a different boundary, we know the velocity changes. Okay, if the velocity changes, what happens here to accommodate that velocity change? Well, does the frequency change across a boundary? In our own lives, do we have experience with this? If you listen to somebody outside a door, if, for example, I'm talking in a deep voice on one side of the door and you listen to the other side, does the frequency change? Does suddenly I'm talking like this? Or even deeper? Does the pitch change when you listen through a medium? I think you'll agree, no, it certainly does not. And right there you have the answer to the problem. Frequency is held constant. So frequency does not change across a boundary. Well then, if the velocity changes across a boundary, the only thing you have that you can change is the wavelength. So what the formula becomes is V is now proportional to the wavelength. So if my velocity increases, what does the wavelength do? Increase. If the velocity decreases, what does the wavelength do? Decrease. They're proportional. So it's sort of like this. So here is a big boundary. Here are some waves coming up to the boundary, and you see the distance between the waves. Now over here, it's a slow medium. And so the waves now can't go nearly as fast. And they would all be clustered together. When they get to whatever device you're using to listen to this, they're still hitting it with the same frequency. Okay? And we understand that the velocity of the wave is then proportional to the wavelength. In this case, it was slow. The velocity went down, so the wavelength decreased as well. In reverse, the same thing would happen if you sped it up. As you speed it up, these waves hit, they zoom out, they zoom out, and they zoom out. So if the velocity increases, the wavelength increases. But the frequency stays just the same. Well, I hope this helps.